Hello, everyone. Today I'm going to be talking about QuaID. It's our tool for detecting and characterizing the variant of concern lineages present in wastewater. So, in general, SARS-CoV-2 wastewater surveillance has been a major topic in the past 2 years, and there are several advantages it offers over just pure clinical surveillance, in part due to earlier detection. Because, again, for somebody to go to a clinic and get tested, they have to probably have some symptoms, and that takes a while they already might be shedding the virus into the wastewater. Additionally, it provides us with wide population coverage, people who might not have access to testing, people who might just choose not to go to the hospital, or people who have asymptomatic cases. So those benefits are great, but of course, wastewater surveillance of SARS-CoV-2 poses some unique challenges. So one of the challenges is the fundamental fact that the RNA viruses require hosts to reproduce and be stable. So RNA just shedded into environment degrades over time. And in general, especially with the emergence of new variants, the primers we use for sequencing can just become less effective. So we might not have this sort of perfect, even coverage that we envision when we think about the clinical sequencing. So those challenges are posed in this framework, and every tool has to address them in different ways. As de facto standard nowadays, FRAE emerged as a sort of standard for wastewater surveillance. It sadly does not utilize indels, something that we rely on. It is partially robust to the degraded data quality in the wastewater setting. It works really great when you have high quality data, and otherwise it starts having some issues, which we'll see shortly. And most importantly, it provides relative abundance estimates. So our perspective with introducing QuaID, our tool, was to design a tool that actually is as robust as possible to the poor data quality that is common in wastewater, and can leverage all of the mutational signatures, so not just SNPs, but indels, which are present in SARS-CoV-2 and are pretty defining for certain lineages. However, in doing so, we do not provide relative abundance estimates. So basically, all tools have trade-offs, and broad recommendation, if you're doing wastewater surveillance, you probably want to use some sort of combination of different tools. So in terms of tracking particular lineages of interest, we need to keep in mind that there are some mutations that are informative and some that are not. And that is always context dependent. So what do I mean by that? As you can see, B1 is the originating lineage of SARS-CoV-2, and we have this big clade that we have the broad name Omicron for, and this deletion in the nucleocapsid gene, between 31 and 33 amino acid, is a very much signature deletion for the Omicron lineage. However, this mutation over here, the spike D614G mutation, is not. So it's common in multiple B descendant lineages. So this is what I mean by some mutations are informative and some are not. So whenever you're screening your samples, you want to have some way of meaningfully distinguishing what works. Also, different things work at different levels. So if you're trying to get to a sub lineage thing, like, for example, we're tracking EG and EG1 or something like that, nowadays that's about 7-8 levels into the tree, so you obviously have much less mutations that can differentiate that, because everything else is in common. And something might be distinguishing at a level, so the deletion in the nucleocapsid does distinguish Omicron from other things. It does not distinguish BA2 from BA1. It's present in both. So with that, we propose the idea of quasi-unique mutations. So mutations that are meaningfully descriptive for a set of variants. We define them relatively simply. It's a mutation that is present in more than half of all the genomes in our lineage of interest, be it Omicron or something more specific like BA.2, or even more specific like EG1. And it's not present in the majority of any other lineage, so in the majority of genomes of any other lineage. It's a very simple definition. You're basically picking mutations that are more likely to come from this lineage rather than any other lineage. And the 50% cutoff is just an arbitrary number. Here, it makes sense, it works in practice, but you can pick other numbers because our code is open and you can tweak parameters however you want. So quasi-unique mutations is basically what we have in there. We can define them for each lineage of interest. And all of that obviously eventually leads to how do we apply all of this. So the data I'm about to show is from the Houston Wastewater Surveillance Project done in partnership with, actually spearheaded by Houston Health Department. The data will be shown basically between February of 21 and May of 22. So this is the data that went into the manuscript. But the program is still ongoing. We're still tracking different variants. And I just wanted to highlight that this is not a kind of one and done project. This is something that is happening nowadays. So it's a map of Houston. We have these 39 wastewater treatment plants that provide us with the data. And I mentioned earlier that one of the big advantages is we get something earlier than the clinical signal. So these stars over here, they show when the first clinical sequence for this variant was deposited for Texas in general. So this is, the bottom stars are not even Houston specific. And what you can see, we were detecting said variant up to 2 weeks earlier. In particular, if you look at the Omicron, you can guess that I didn't have the most fun Thanksgiving in the year of 22 because Omicron. Actually, year of 21. And what makes this early detection possible? So I mentioned early on that we're one of the few tools that tracks down indels. So very early this morning, Dr. Sedlajic mentioned that his area of focus is structural variation. So indels are basically variants that are not just one nucleotide change, they're either insertion or deletion of a slightly larger fragment. And as you can see, this deletion that is characteristic to Omicron, the nucleocapsid 3133, is one of the leading signals that we had that enabled us to detect the presence of Omicron in Houston wastewater early on. So if we didn't have this column and a couple of other deletion columns, we actually would have missed most of the early detection and we would have not had that early warning capacity. So this just highlights the importance of utilizing all mutational information, not just the SNPs, for this kind of applications. We also investigated how robust we are to dropout and general sort of degradation of the data. This was an early simulation, a simple one. We retain only 10% of all SNPs, and we see whether we can pick up whether a variant is present or not, and whether Freya can pick up whether the variant is present or not. You can see that the top essentially picks out nothing, so Freya doesn't detect any variants of concern, and the dots at the bottom are cases where we actually pick out some data. So this is a more sort of detailed view where we try different levels of dropout, and consistently we have generally better sensitivity in this framework. However, this is a very simplistic simulation, so afterwards we decided to go forward and conduct a more comprehensive simulation on a range of variants and scenarios. We found that actually in this more robust and extensive simulation framework, QuaID tends to be more precise rather than sensitive, which was quite surprising to us to a degree, but also is an important thing to understand because in public health setting, we might prefer a tool that doesn't raise false alarms and actually is accurate whenever it calls something out. In particular, this is the result of about 32,000 simulated samples across 104 time points, and those samples were simulated using real wastewater data as the sort of coverage profile. So we essentially guided our simulation by the degradation profiles we observed in practice. So, which is why we tend to believe that the results shown by these simulations are quite important. So a little bit more data from the simulated experiment. We can control, because one of the things that gives us superior precision is using multiple variant callers and utilizing the sort of consensus variant calls in the sense that the ones that were produced by multiple variant callers in our analysis. We can relax that condition and only use one of them. That increases our true positive rate, but sacrifices our precision. So again, this is something that we think is important to bring out to the user and discuss, because if your setting does not care as much about precision, you really just want to detect things, and then maybe you have some sort of follow-up method to control for your false positives, you can tune that, and again, our tool allows you to tune that to your application. So this is one of the sort of benefits of this open source framework for this kind of work. Also, just to kind of bring back the point about the deletions, majority of the samples we work with have poor coverage. Again, environmental degradation. However, the region around nucleocapsid gene is pretty well preserved. Again, data-based pattern, but that gives us sort of more confidence that this marker is actually a useful marker, because empirically, this region tends to be less degraded in the data we have, and since we have a marker there, we're more confident in making these Omicron calls. So in the conclusion, we have a fast and robust method for determining quasi-unique marker mutations for lineages of concern. We can efficiently and accurately detect emergent SARS-CoV-2 lineages from wastewater data, and this method is currently employed for routine surveillance in Houston. I would like to thank lab members of Trengen Lab, and in particular, Dr. Mike Newt and Yunshi, who's present in the audience, members of the Stadler Lab and Lauren Stadler, as well as Catherine Anzer and our collaborators from Houston Health Department. You can access the software at the GitLab link and the manuscript at the paper QR code. Yeah, and that would be all. I'll take your questions.
Especially impressive given this was a very last minute swap in. Any questions for Nick?
I was just wondering what it would take to get, you see the table you made about relative abundance, what it would take to make your tool have a yes for relative abundance?
I'm sorry, I didn't catch the very last part.
On your tool, there was a table at the beginning. Maybe I missed the reason why relative abundance wasn't checked. Yes, I was just wondering what it would take to get relative abundance.
Yeah, so this is a very, very good question, and I'll repeat for the audience if somebody didn't catch it. So early on, I showed this table, and there's this nice feature that Freya has, and it's estimating relative abundance of these lineages. And what it would take, so the question is what it would take to get that information added in here. And I will say that in our particular case, it's an explicit design choice to not have that information, because we believe, based on our extensive simulation and experience with the data, that reliable estimation of relative abundance is impossible. The data just simply does not allow you to do that by its own nature. If you have high quality data, so if, like, let's say environmental degradation happens, yet you have very, very robust set of primers, and you have very robust sequencing protocol and so on, and your data is indeed high quality, you can essentially employ a very similar framework to what Freya does with quasi-unique mutations. You will need to add a few caveats because quasi-unique mutations have a little bit more overlap, so there is a little bit more quirks in the optimization framework that Freya uses to disentangle that. That being said, we believe that the data as is, and data as is not just in Houston, but in most wastewater efforts across the country, is just simply not suitable to make that inference reliably. You can make that inference, you can get the results, you can say something about them, but we just do not think that that data should be trusted. So, yeah.
Yes.
So the framework support for which languages? Framework support for which language? I see the software in the GitLab. It support for which language? Python or C++? Or
Oh, yeah. So this was written in Python. There are parts of it that rely on other tools written in like variety of languages, but essentially everything you need to run this can be installed through Conda. This thing itself, the QuaID itself is written in Python, and we do leverage, so there's a step that I kind of hid in the background here, but as Dr. Hansen mentioned earlier, COVID generated a lot of data. So there's 15, maybe 16 million genomes floating around nowadays. So in order to process that, we leverage specifically the desk library in Python, because processing large amounts of data and extracting stuff from that requires a little bit more specialized libraries than what you typically find in data analysis, like more basic data analysis in Python. But yeah, most of it is written in Python.
Thank you.
Thank you for the great talk. My question is regarding, are you aiming in the future to expand your tool for other viruses beyond COVID, or you will stop here? Thank you.
That's a great question. I think we intend to extend it to other viruses, and potentially not only viruses. I mean, bacteria are quite common in wastewater, and wastewater tends to be a reservoir of antimicrobial resistance genes. That being said, it's probably not going to be me continuing said work, so that might be kind of a broader question. One thing that I will say, though, is some of the particular challenges of this project, but also some of the particular power of this project, comes specifically from the amount of data we have for SARS-CoV-2. So I envision that for some viruses, this might be easier. I think for flu, we have a reasonable amount of data. For some viruses, especially sort of more rare, less tracked viruses, a project like this might be much harder to achieve just because the publicly available sort of standard of data is much, much smaller. So, yeah.
I see. Thank you.